Okay. Oh, it now works. Okay. Okay, thank you. All right. Good morning, everyone. I'm impressed how much on time you all are. Wish that was the case in the Netherlands sometimes. Third day already of our course, and you've been learning already a lot, and we'll learn more today. With a brief summary of very quickly of what we've looked at so far. So we studied in some detail how to construct a gauge theory. We elevated the principle of local symmetry to a guiding principle, and that led us to the covariant derivative, and with that we can construct the matter sectors, so how gauge theory interacts with fermions or scalars. Once you have the covariant derivative, it's easy to do. Even the field strength, the kinetic term for the gauge fields themselves, you can make through the commutator of two covariant derivatives. So the covariant derivative is at the heart of it all. And we studied also the symmetries. Well, if you use a covariant derivative, the local symmetry is built in. But for QCD, we also look at some accidental global symmetries that appear because you have more copies of the fermions. You have up, down, strange, etc. And you can mix those in flavor space. Those are global symmetries. There are more symmetries, but we will not, global symmetries, but we will not discuss them. So we learned to do this in both in a Lie algebra value, a bit of an abstract notation, but also in components. And from the Lagrangian, we extract the Feynman rules, and with those we can then make Feynman diagrams. And the Feynman diagrams will be a large part of the attention of the rest of the course. Not completely, we will use some field theory here and there, but we will be mostly concerned in how to understand Feynman diagrams and the cross-sections and the amplitudes that you build from them. And in fact, we did compute the Drell-Yan cross-section at tree level, at lowest order. We saw already yesterday that the lowest order and tree level is not always identical. Often it is, but there were a few processes such as Higgs production, such as pi onto 2 gammas, where lowest order is already at one loop. Compute Drell-Yan at leading order cross-section in the context of the Parton model. There the essence, I mean the picture is really quite easy. You compute the hard scattering, the scattering of the partons inside the proton, and when you're done, then you combine it with the Parton distribution functions, the PDFs, to make the hadronic cross-section. I gave you some notes also on this. I hope they clarify things a little bit. If not, let us know. We're happy to, also together with Anuradha, we're happy to try and repair that, maybe in the context of deep elastic scattering. So this is all tree-level leading order, and I think now it is time to go to higher orders, and particular loops, loop diagrams. Some of you may have had some of this before. I hope it won't be too much of a repetition, or that you at least pick up some new things.
Can I move the blackboard to the center because the camera is still not on?
Oh, right.
If I just bring that one to the center?
No, let me just erase it then. Just wait until the camera is on. This is. So let me continue at least with this blackboard. Right, so the topic will be higher orders, dimensional regularization, often called abbreviated as DIMREG, and ultraviolet divergences. And they occur when you have loop diagrams. Feynman rules tell you that you should combine them in all possible ways to construct a process of interest. And you can have, for example, a diagram like this. A one loop diagram, say in phi cube theory. These are phi cube vertices just to illustrate the point. For example, here is momentum P coming in. Here goes P plus Q. Q goes back there. And then P goes on. So momentum is conserved. But Q can take any value. There's nothing that restricts the loop momentum Q. And the contribution of this diagram goes in principle like d for Q over 2 pi to the 4th. And then there were two propagators. Since it's scalar theory, they're really quite easy. Q squared plus m squared and Q plus P squared plus m squared. Right, so that's easily written down. But you already see that since there's no restriction on the Q momentum, in a certain region of the loop momentum space, the Q values will be very, very, very large. So we can neglect M, we can neglect P. These are fixed values. And then, so in the region where Q goes to infinity, this starts behaving like d for Q over Q squared. And this we can write as a three-dimensional angular interval times Q cubed dq over Q to the 4th. So I use polar coordinates in 4 dimensions. This is not necessarily Minkowski space, it is just an interval over all space.
Take 5 minutes.
Okay. So I'll just keep on working on this board for the time being.
So the right side is not visible.
Yeah, that's right. For you, it's hard. Let me just copy it. It's visible until here. Okay, well, so this is Q cubed dq over Q to the 4th. And this will be this is 4 pi squared, and then dq over Q. Now you see more clearly that this is a logarithmic divergence. So when this goes to infinity, this is the size of the 4-dimensional momentum, Euclidean size if you want, and clearly this is divergent, right? A logarithmic divergence. This is a UV divergence. And these typically occur in loop diagrams, certainly not all loop diagrams, and we will learn to recognize roughly in which loop diagrams they would occur. But nevertheless, they do occur. And now, one possible way of proceeding is not to proceed, is to say, okay, obviously when you go to higher orders, there are infinities, the theory has no predictive power, let's go and do something else. Like play tennis or something like this. But you can also see if you can do something with it. And in fact, it is possible, as many of you know. You can handle these divergences, but to do that, you must first learn to manage them, to make them temporarily finite in a consistent way, such that you can work with these would-be divergences, hopefully cancel them, and then remove your regulator. So, to work with divergences, regulate them. And here we have a number of choices. So just a few methods. So let me put a bar here so I know I shouldn't go beyond that. Okay. One is, so I'll just do it here, methods, or one is a cutoff. So you just have this integral dq over q, and you just by hand impose an upper limit on it, called big lambda, that clearly regulates the divergence. And this gives you the would-be divergence in the form of log lambda. Would be in the sense of if I remove the regulator by letting lambda go infinity, it reappears. This is certainly often used. This is not a bad one, particularly for pedagogical purposes. So it's the positive aspect is quite physical and intuitive. The negative aspect is hard, very difficult to use in practice. There's a famous law of conservation of misery. This is when you have something good, something bad comes along. So that's one method. A second one, can I erase?
We'll take a picture of the blackboard for the video.
Oh, I can't do Control Z now. Someone taking a picture?
I'll
Okay.
take a picture of the blackboard.
More or less restored it. Oh, that also work. Yeah. Okay. I'll leave it as a puzzle. What were the first two letters of that word? Okay. Can I erase? So a second method is not to put a cutoff on in momentum space, but to discretize spacetime. So to work on the lattice, where inter-lattice distance is a lattice spacing. It means that all momenta are restricted automatically to values below 1 over the lattice spacing. So that's an indirect way of imposing an upper cutoff on the momenta. And here also, there's positive aspects. This is very good for computers. So even non-perturbative calculations are possible. Lattice gauge theory, lattice QCD, is a very impressive field in and of itself. The negative aspect is that it's hard to maintain symmetries. We rely a lot on space-time being continuous to understand our symmetries of Lagrangians, and if it's discrete, you have to think a little bit harder, and some are really tough, like chiral symmetry. And then finally, DIMREG, which I will introduce, of course. Basically what you do is you change dq over q to dq over q in the 1 minus epsilon. Because you see, it's just at the criticality of being divergent. If this exponent was a little less than 1, sorry, a little larger than 1, I should put a plus here perhaps for, then it is finite. Right, so that's more or less what it amounts to. Of course, we introduced it in more detail. Here, the negative aspect is less intuition. That is just a fact. But the big plus is that it's excellent for calculations. So that's the one that everyone uses, more or less. So I'd like to introduce some details of it. Can I erase? I don't think I should write smaller, right? In the back it's probably just this. Is this the right size? It shouldn't be smaller. No. Oh, there's another board here.
Yeah, this will come up.
Was that a whiteboard? Sorry? Is that a whiteboard or a blackboard? Okay, so well, she knows all the details of operating that, right? You were very good at this yesterday. Yes. So let's look in general at field theory in n dimensions. Okay. And we'll just do some basic dimensional counting. Maybe many of you have seen that. It's maybe good to do it quickly. I'll indicate with square brackets the dimension of something. So we choose units where the dimension of h bar and the dimension of c are 0. They're just 1. The number we set them equal to 1, so they have no dimension. In that language, we have that the dimension of energy is the same as the dimension of momentum, which is the same as the dimension of a derivative, is 1. We also have that the dimension of the action, dn, is 0. Action should be dimensionless. It occurs in the exponent in the path interval, 1 over h bar, but h bar is also dimensionless. So this means that the dimension of the Lagrangian must be n, because the dimension of the measure is minus n. So from that we have that, so for bosonic fields, say we can just be very sloppy. d phi is the typical term in the action. That means that the dimension of the bosonic field is n minus 2 over 2. Sorry to put a phi. And for a fermionic field, then we typically have something like this, so that the dimension of a fermion field is n minus 1 over 2. Now, for the dimension of the coupling, we also have that E psi A psi, that dimension is n, right? That's the whole term in the Lagrangian. And to get the dimension of E, we just have to subtract from n the dimensions of the two psi's in A. So here, follows that the dimension of E is, I'll leave you to check that, minus n minus 4 over 2. So it's dimensionless in 4 dimensions, but has some dimension if you're not in 4 dimensions. Okay, so often, in fact, we shall introduce, one introduces a mass scale, an arbitrary mass scale, mu, so a dimension of mu is 1, to make dimension explicit. To make dimension explicit. So, for example, we can write E as e to the mu in the minus epsilon over 2, where we define n minus 4 equal to epsilon. So when epsilon goes to 0, we're back in 4 dimensions. And this makes the scale explicit. So this E, in fact, will make it mu dependent, because the left-hand side is not dependent on mu. Here I have, so this must also depend on mu, such that the product is not. It's a bit implicit definition, but this one is dimensionless. This has dimension. Okay, so much for the very basic things. Is this very familiar? Somewhat familiar? Okay, mixer. Okay, and let's continue here. So now we return to our Feynman integral. Am I being followed? Not yet. There we are, yeah. Let's look. I is the integral dnq, so we're in n momentum space dimensions now, 1 over q squared plus m squared squared. Let's look at this particular one. Notice that n only appears here. The propagators stay as 1 over q squared. It's not 1 over q to the n or something like this. They stay as 1 over q squared. So in the dimension of I is n minus 4. Of course, you can immediately see that. And what we'll do is we'll learn to compute this. So what we'll also be looking at in n dimensions, as long as we're defining things, is the gamma matrices. We need those for spin 1/2 fields. Gamma mu, which run from 0 to 3 in 4 dimensions, and now we have them from 0 to n minus 1. In such a way that the anticommutator of 2 of those is 2 eta mu nu, where the index mu and nu also here run from 0 to n minus 1. We think for the moment of n as an integer. By the way, also, just to, this is n. This counts the number of dimensions. Now, there is a whole theory of, a whole setup of representing Dirac matrices in higher dimensions. Particularly people working in string theory need to know that. And typically then the dimension or the size of gamma matrices in n dimensions is 2 in the power n over 2 entier by 2 in the power n over 2 entier. So that's the modulus. So it's 4 by 4 in 4 dimensions. It's also 4 by 4 in 5 dimensions. Jumps to 8 by 8 in 6 dimensions, etc. And still 8 by 8 in 7 dimensions. So that means that really here there is a secret unit matrix, because these are matrices. This matrix has normally this dimension. Right. Now, the very nice and consistent simplification. So we use that trace of this unit matrix is 4. So we extend the vector indices to n dimensions, but we keep the spinor index at 4 dimensions. So that is a consistent way, certainly for non-supersymmetric theories where the number of fermionic and bosonic components must match each other. Here they're typically unrelated. So here we can set this to 4 just to reduce the number of n's that start appearing everywhere. Okay. The only problem, by the way, in n-dimensional regularization is the gamma 5. That is a typical 4-dimensional object and leads to all kinds of interesting stuff, but we will not discuss that in this course. So this is a bit the setup. Let's now go to consider an actual integral. Favor the people on this side of the room. So define a bit more general form of the Feynman integral, n alpha to be the n-dimensional integral 1 over q squared plus m squared. And you introduce the small imaginary part here, epsilon, to the power alpha. Now, this is finite for n smaller than 2 alpha, because then the integral is not as bad as being logarithmically divergent. Now, this integral has poles in the, so for the Q0 integral, if I split this into a Q0 integral and an n-1 dimensional integral, there are poles at Q0 is plus or minus equals plus or minus the square root of q vector squared plus m squared minus plus I epsilon, which I will also write as plus or minus omega minus I epsilon. Omega is the square root. Right? Have you ever, as people, seen this before? Not ever seen this before? I mean, it's important to say this because that determines a bit what I say and how fast I go. Has it ever been seen? You've seen how the poles are extracted here? Yeah? Okay. So if I draw them in the complex Q0 plane, after the little imaginary part indicates, treat all these n integrals as complex integrals. That's an instruction, a reminder to yourself. And these poles here are in the 4th and the 2nd quadrant. And here goes your Q0 integral. So more or less like that. What you can then do, and there's more details in the notes, is to, because you must decide how to do the integral, what you can do is you can rotate the Q0 contour over I to go along the imaginary axis in a certain direction. You must go this way, not this way, the poles obstruct that. And that, so it's a Wick rotation. You replace Q0 with I, QE. And QE goes along the imaginary axis. And then, if you do that, then n of alpha is I, that's a Jacobian factor coming out. And then you actually have an n-dimensional Euclidean integral, 1 over q squared plus QE squared plus m squared. I'll move out of the way to the power alpha. Right, so that the poles have taught me how to rotate such that you now have a much more symmetric integral where all n components are treated in the same way. not zeros separately from the n-1 vector ones. Now in the notes, I will not go through all the details of that. One can see how to compute this. It is not too hard to do. You have to make this, again, a polar decomposition in the number of angles and the radial coordinate. The number of angles is sort of an iterative thing. It constantly gives you signs of these angles theta. But you can always represent them as Euler gamma functions. The Euler gamma function, there's a few things in the notes about that too, occurs all over the place in dimensional regularization. You need to be a bit familiar with it, but it has such nice properties that it's certainly not a punishment. Also then the radial coordinate over Q can be written as an Euler gamma function. And what I'll do is I'll just give you the answer. So I of n alpha is I pi to the n over 2, the gamma function alpha minus a half n over gamma of alpha m squared n over 2 minus alpha. That's it. Nice, clean, simple result. Where alpha must be larger than 1/2 n for consistency. You also see here, I mean, I always try to make you read formulas such that you can see a little bit structure in them. You see here if alpha is equal to a half n, suppose n is 4 and alpha is 2, we know we have a logarithmic divergence and it shows up as a pole in the gamma function. You know, gamma function has, so gamma of z has poles at negative integers. And these poles are the sign of a divergence. I'll say more about that. So this is very typical in a dimensional regularization. So we have poles when alpha minus a half n is smaller or equal to 0, and zeros when alpha is smaller or equal to 0. This almost never occurs. Typically you have alpha a positive number here, but should you decide to make it negative for some reason, then it can be that you get zeros because you have 1 over a pole. Now, this drawing and this result gives you a bit of an indication how to regularize this. So if n were an integer and alpha were an integer, it seems a bit useless to have this nice form. Then you can just write factorials. But so note, if alpha minus a half n is not equal to a non-positive integer, that's a double negative, so if it is not sitting exactly on these poles, then you're okay. So that says treat n as complex. So we take n as a complex number. Of course, immediately that throws intuition out the window. How can you imagine yourself to be in 3 plus 4i dimensions? But we deal with this at the level of integrals. And intuition doesn't matter. We're trying to deal with integrals in a consistent way, and that's fine. So when this is a complex number, you could say, well, here it's fine, and then if you approach this, well, we just go in the complex number around this way, and things should be fine. Where you then use the full strength and the power of the analytic behavior of the gamma functions to treat your Feynman diagrams. So in that case, divergences are simple poles. For example, we have that 2 minus gamma of 2 minus n over 2, that would be the case if alpha is 2, can be written as, and we use here the property that z gamma of z is gamma of 1 plus z. a very nice property of the gamma function. What I can do is take this gamma and its argument here, multiply by it and divide by it. Right? If the multiplication will raise this by 1, and then divide this, then I get 1 over 2 minus n over 2 times gamma of 3. I couldn't even add 1 to 2. It's 3 minus n over 2. And you see here, when n goes back to 4, we have here a pole. So we can write this as 1 minus 2 over epsilon, gamma of 1 minus epsilon over 2. Right, if you remember what epsilon was, epsilon is n minus 4. So that's what you get. So you see really a pole in epsilon. When you go back to 4 dimensions, immediately your divergence reappears. This thing, of course, is fine. A gamma of 1 is 1. So this is fine now. But you've really, thanks to this rule, you can make the poles very explicit. This is something to appreciate, that in many other regularization schemes, such as cutoff regularization, you have logs of lambda, lambda log lambda, also divergences, but then you're dealing with logarithms, branch cuts. It becomes very complicated. So in this method, you will never find a log of epsilon or so, or log of, or something, and some other function with branch points. It's just the pole. Negative or positive powers of epsilon. That's extremely powerful, and that's really at the basis of why this method is so popular. I do want to address one other point to illustrate a fine point of dimensional regularization that even those who've had it before may not have seen. And it's a brief point. So it's a region of validity. So we have now that dimensional regularization for I n alpha is valid for n smaller than 2 alpha. So that's a bit of a restriction, and we'd like to free that up. We'd like to see, can we extend the range in which we can use these methods and these formulas to other values of n. So this is then the little section on analytic continuation. Of dr dimensional, I even abbreviate dimreg to dr now, and I will stop abbreviating then. Dr integrals. So the trick is kind of nice. It says use the following identity, the n-dimensional integral of ddq mu of q mu times some function of q. We can work this out. This can act on q mu, that gives n, and it can act on f, of course. So this is equal to dnq q mu ddq mu on this function f of q plus n times dnq of f of q. That's a fairly obvious identity. Now, the method now comes from setting the left side to 0. So the left-hand side equal to 0. This is not a trivial statement. You think, oh, it's a total derivative. How can it not be true? But it could be that this f of q is is badly behaved at q is infinity. Then we shouldn't do this. But in dimensional regularization, you can still say that. You posit as a rule anyway. You're not doing mathematical integrals. You're defining a calculational scheme, and sometimes they are a little weird. As long as the rules are consistent, and the rules are consistent to say we define the left-hand side to be 0, even if the integrand doesn't seem to be falling off fast enough at infinity. So 0 on the left-hand side. We also take f of q equal to 1 over q squared plus m squared to the power alpha. That's not a shock, that's what we were working with. And then, just from this identity, you just work it out, and there's a few more details in the notes. You find that dnq 1 over q squared plus m squared to the power alpha is equal to, it follows from 0 equals this plus this, is alpha m squared over alpha minus a half n dnq 1 over q squared plus m squared to the power alpha plus 1. I invite you in the tutorial session just to work that through. It's just a 1 or 2 lines. Now you see this is the thing we were working with, and again it has a pole at when n is 2 alpha, as we had found before. And you can still see that in the argument of the gamma function. But it is now expressed in terms of I n alpha plus 1. And this thing is valid for n smaller than 2 alpha plus 2 because of the extra 1 in the index. So we've extended the integration or the validity domain of n. You don't have to be smaller than 2 alpha. It's okay to be smaller than 2 alpha plus 2. And in fact, you can iterate this. You can go on to infinity.
Where did you get that condition, the n minus 2 alpha?
Oh, that is from just from the basic form. If you look here, so a very large q, you see it's q to the power 2 alpha, and you have n integrations. So it is, if n is smaller than 2 alpha, it is not even logarithmically divergent.
Here you talk about poles, so the integral is divergent, isn't it?
When n is precisely equal to 2 alpha.
Okay.
But if it is not quite, then it is not.
Yeah.
Okay. Okay. So this is just a way of extending the region of analysis, so we can now drop this condition because we have a way of making the formula valid for arbitrary n.
This is some kind of Gaussian theorem on the LHS.
Well, it's certainly, if it's a convergent integral, it's Gauss's theorem. If there's no enclosed divergence, it's 0. But we set it to 0 even if it is a divergent integral. That's a bit different. Right. So I've been working here with n and alpha, but I'll move more and more to the language of epsilon, the difference from 4. And there's a few useful bits to know. So I'll leave that formula in, I'll erase the rest of the board. So let's take alpha equal 2. Then we get I pi in the then we have 2 plus a half epsilon, gamma of minus epsilon over 2. Gamma of 2, who knows what gamma of 2 is? 1. Gamma of 2 is 1 times gamma of 1, so that's also 1. And then we have m squared to the power epsilon over 2. Now, just a few things one typically does in the dimensional regularization. We had already seen that this can be written as minus 2 over epsilon gamma of 1 minus epsilon over 2, just by using that same rule. We had already seen that. Often what you do is, what do you do with things to the power epsilon? You need to see it once and then you know. So and this is always written. Remember, our goal in dimensional regularization is to make Laurent series in epsilon, things that are negative or positive powers of epsilon. And this does not look, this has some exponent epsilon. So how can we make this into the series in epsilon? Well, you can write this as E in the epsilon over 2 log of m squared. And then you expand the exponent. So this is 1 plus epsilon over 2 log m squared plus epsilon squared over 8 log squared m squared, etc. So that's not so hard. You see here also how logarithms come into the game, and that'll occupy us certainly quite a bit in the rest of the lectures. In dimensional regularization, logarithms always arise from things to the power epsilon. And when you combine, when this is all multiplied, this is the nice thing of Laurent series, you just combine the poles and the positive powers. So in the end you want a physical result has epsilon to the 0. Because when you're all done, you're going to take epsilon to 0. If you're left with one over epsilons, you have to think first. Oh dear, my answer is still divergent. Have I missed something or not? But if your final result is gauge invariant and also has only positive powers of epsilon and hopefully also a 0th power, set epsilon to 0. But if you multiply this, you see that this 1 over epsilon can multiply this power of epsilon, leaving one logarithm. You will not get a log squared in the answer at this order, because 1 over epsilon with a log squared gives an epsilon squared that leaves one power of epsilon left. So when you set it at the end to 0, it's not there. However, if you would do 2 loop integrals, you would have double poles, you get log squareds. If you have 14 loop integrals, you get log of the 14th. So it's really quite easy to keep track of divergences and logs in dimensional regularization. Another one we'll often use is that you can write the gamma function. Let me write the following general form of the gamma function, where eta is small. Right, I'll write an exact answer. It is the exponent of minus gamma e eta plus the sum of n is 2 to infinity eta to the n over n zeta of n. So this is an expansion in the exponent of this small parameter eta. Here eta is minus epsilon over 2. And you see here the Euler zeta function. Zeta 2 is pi squared over 6, etc. You maybe know that Euler zeta function. You also see this gamma sub e. Who knows that number? Yes, so it's called the Euler constant, or Euler Mascheroni constant. So gamma of e, it's just one of these constants in math, just like pi or e, and many other digits. It always appears at intermediate stages, but it never appears in a physical answer. And why is that? Why would you say that? I'm telling you this, right? So, you clearly see that gamma e's can appear, but they never appear in a physical answer. Any thought as to why that might be?
Integrals are defined to within a constant, so in defining integrals to within a constant, there's always a factor.
No, that's not quite the reason. No. You can handle them somewhat in that way, but that's not really why they never appear. No one has a thought? Just guess something.
Some other part of the integer also appears exponential plus gamma e times eta also appears from some other part and cancels out.
That often occurs, but that is more of a mechanism, right? And so is there any fundamental reason why it wouldn't appear that you could think of? So, well, let me just tell you, we're dealing here with a regularization scheme, dimensional regularization. And this gamma E really is intimately tied to having these order gamma functions, which is intimately tied to using dimensional regularization. So it is an artifact of this particular way of regularizing intervals. I could have chosen another one, cutoff, much harder, but no gamma functions appear there. So it stands to reason that since it's an artifact of dimensional regularization, it appears in intermediate stages, but in the very end, when you remove the regulator, it should not be there. In fact, it won't be. But it's good to realize these things. Good, so this formula also allows you to compute, expand, so we've known how to expand this m squared to the epsilon in powers of epsilon. The same goes to pi here, right? It's a power of epsilon, we can expand that. And we can now also expand the gamma functions in epsilon. So we have all our tools to create poles and positive powers of epsilon. So then, if you work this out, then I n of 2 can be written as minus 2I pi squared 1 over epsilon plus a half gamma E minus a half log of 4 pi plus order epsilon. I wrote it down also because this particular combination, 1 over epsilon plus a half gamma E minus, that comes from here and from the gamma function, that always occurs together, this combination. For those who know, that is then often taken as the finite parts that you include together with the pole to define the MS bar scheme. I'll say something more about that later. So we have here a method, dimensional regularization, with which we could regularize loop integrals that would be divergent. We've analytically extended it. We've already seen some of the math that helps you express your result for the integral as poles or positive powers of epsilon, and we find logarithms. Let me make a few remarks about the scheme. Some further remarks on dr. One is more loops, higher powers of 1 over epsilon, or higher poles. So, for example, if you have such an integral in pi cube theory, this produces not 1 over epsilon, but it produces a 1 over epsilon squared, but also 1 over epsilons, etc., and constants, and positive powers of epsilon. But the worst pole is 1 over epsilon squared. If you have, as I said, 14 loops, you get 1 over epsilon to the 14th. You also have some identities, and these are basic integral identities, but actually formally people had to reanalyze those in the context of dimensional regularization because of these strange statements that this is 0 no matter what the behavior is of the integrand. You have to rethink all the things. Can you shift a variable under an integral? Okay, is that okay? And the answer is yes, all these rules are okay. But someone worried about it. In fact, the proofs go through analyses in large negative dimensions, so in -4 and -5 dimensions. Try and imagine that. I certainly can't. So also, but the nice thing is nice symmetry properties like this. This is immediately 0 because this is odd in Q. If I flip Q to minus Q, I get minus this integral, so it's 0. I also have, if I use my invariant statement, suppose I have 2 loop moment is standing there free. That's not 0. And if I change q to minus q as a change of variables, I get positive. It's the same as this. So what is this? Well, it must be something times eta mu nu. That's all it can be. There is no momentum inside the integral that you can use. There's only eta mu nu to make it symmetric to an extensor. How would you find A? Contract both sides of eta mu nu. That's actually quite nice. Here you get A times m. Here you get q squared. And then what you do, you write q squared is q squared plus m squared minus m squared. And then you have two instances of this formula. So it's nice and quick to do. Here's a subtle one. This is when m is 0. And this is again one of these consistent definitions of dimensional regularization. D and q. 1 of q squared to the power alpha is 0 for all alpha. This is by definition. Also known sometimes colloquially as massless tadpoles of 0. This would be a diagram where you'd have just one propagator, q, going around. And it looks a bit like a tadpole, a young frog. So this is certainly a bit surprising. Right? If alpha is minus 100, it's 0. If alpha is 2, it's 0. For more reasonable values of alpha, so as you can imagine 1 or 2, you can show in a little bit more detail what happens then. Then you see that actually it has two divergences, one on the small q, one on the large q side, and they cancel exactly. But the statement is consistent for all alpha, even when you cannot imagine it anymore. And this is really useful because QCD is full of massless particles, and if you occasionally occur an integral where the mass disappears, set the whole integral to 0. So we learned a lot about integrals of this form, right? I and alpha. And the question is, can you bring every integral that you find in loop integrals to that form? The answer is yes. So can we bring integral expressions to the form I and alpha? If not, we have to do the whole thing again, because most loop integrals look different. So, for example, we have the example we had before. We had here p in, p out. Here goes p plus q, and q goes back. Then we have d and q over q squared plus m squared, and 1 over q plus p squared plus m squared. Often I drop the minus I epsilon. It's always implicitly there, but I just won't write it. So this does not look like this form I and alpha. The key point of this expression for I n, there was one denominator. Here it was, so you had 1 here, it was just one denominator. Here we have 2. So here's a nice trick, a very important trick, by Feynman. Who else? And it basically says if you have two denominators, let's call them a and b, I can write this as an integral from 0 to 1, 1 over xa, 1 minus xb, And you prove this just by working it out. It's a tiny exercise. So what this does is if you had a product of two denominators, you now have one denominator squared at the price to pay that you now afterwards must integrate over a new parameter. That's the conservation of misery kicking in again. You did something nice, but you have to be paid back. So you can use this trick to combine these two. And one other nice thing is, look here at the q squared. Q squared plus m squared. This is q squared plus 2p dot q. This term will get an x. This thing will get a 1 minus x. If you add them up, the x in front of q squared vanishes. It's just q squared times x plus 1 minus x. So you again have nicely the form here. There's a regular q squared. Now behind here will stand stuff with x inside. But at least you can do the integral now. Call this, whatever this is, n squared. It needs to have a name. And then afterwards you must then figure out how to do the x integral. That's not easy. But at least you're off the board and you can start actually calculating things. And there are examples in the notes of that. I'd like to conclude, I guess, this morning's session with generalization of this, because one of the problems for the tutorial is that you will struggle a bit with the general form of this. For more complicated integrals, you need generalizations of this. At least it's useful. There are generalizations when you have 3, 4, and 100 denominators, also the different powers. I'll write down the formula in a moment. But I'll give you one bit of advice. Suppose you have to do a triangle integral ever in your life, like so. And there are 3 propagators. You have a, b, c that you then must compute. You will need 2 finite parameters. We'll see that in a moment. And the temptation is always then to use the formula for when you have a, b, c. But there's a second possibility that you work pairwise. That you first combine 2 denominators to a combined one with 1 finite parameter, and then you combine this denominator with the third one with a second finite parameter. So the 2 plus 2, the consecutive rule of using 2 denominators versus immediately going to 3 can sometimes be useful. The 2 are equivalent, of course. You can map one into the other. But I found always practical that it's often convenient to use this rule and its generalization. So here is the general. Let me write this on the new board, and this will be in the notes. So if you miss it now, it's not a huge problem. It's a beautiful formula, very powerful, at the basis of a lot of modern developments in higher order calculations. And it's actually so nice I can do it by heart. So you have a1 to the power alpha 1 to an to the power alpha n. That's a general form. And n denominators to some power. And this will begin with the sum over all the gamma function of the sum of all the alphas divided by the product of the gamma functions for each alpha. Then we have finite parameter integrals. We have n of them. We have n denominators, n finite parameters, all running from 0 to 1. Then we have a denominator, x1 in the power alpha minus 1 to xn alpha n in the power minus 1. And then a restriction on all the x's, 1 minus x1 minus xn. So the sum of all the x's must be equal to 1. And all of this divided by one big denominator, x1 a1 plus xn an to the power alpha 1 plus there it is. Not even that ugly. What it does is the product of all these complicated denominators becomes one big denominator. to, of course, to a much higher power, the sum of all the immediate powers, and the expenses that you now must afterwards, this allows you to do the momentum interval, the q-squared interval, but afterwards you must then still do all the time draft intervals, because those are often tough as well. You can easily check that our formula there is the limit of this for two denominators. Okay, so what we'll do after the break in the next lecture is, now that we have a lot of technology for doing loop intervals and extracting the divergences in this very nice scheme, dimensional regularization, where all divergences are poles, we can then start to see if we can make sense of the quantum field theory, whose diagrams produce the divergences. Can we account for them in a way that maintains predictive power? Can we normalize the theory to make the theory finite? I'll do that first conceptually and then with a few examples, and then from then on we can use renormalization group and all that stuff, so that will be useful for QCD as well. This is general field theory still, so at least now I think the tools are here for this, for dealing with loop intervals. I should also say that this dimensional regularization has even more benefits than just regularizing ultraviolet divergences, because we'll also encounter infrared divergences and even something called collinear divergences, and wouldn't you know it, the same can be regularized by dimensional regularization. So we don't have to think of another regularization scheme. You could, but then you make life needlessly hard. So if you work in n dimensions, you regularize the infrared divergences and the collinear ones too. We'll see that later in the course. So it's really worthwhile having devoted a bit of time to dimensional regularization. Are there any questions? Needs to sink in a little bit. Yeah?
Sir, I had a question that you said that the extra dimensions have not to be an integer, like that epsilon that you have added.
That's right, can be complex number.
So if I had extra dimensions, say I was working in 5 dimensions, then will this procedure help me?
Yes, but for certain cases you can see if you can smoothly go from 4 to 5, see what that does. It depends a lot on the situation. There's no general answer to give, but it's not that you could say, look, I'll do all my things in a 4-dimensional theory, and if I want interested in extra dimensions as a physical extra dimension, all I do is use these formulas. That's not always true. There are things that you maybe want to address that are extra in 5 dimensions, extra domain walls or something like this that are not appearing in this. There's no interesting structure in the extra dimensions in this way of doing it. You may want to put curvature there, or that you don't have here. But in other cases it can. Even in certain cases, when you have linear divergences rather than logarithmic, you can think of going to 3 dimensions where the linear divergences become logarithmic again. And then that can be useful. But this is really just a regularization tool and not really something to address physical problems with. Okay? Shall we have some tea?
He is right here today. So don't put the other side, that is some other conference.